Good evening, everyone. It's not commencement yet, but great to see you here at the big commencement auditorium tonight. And welcome to the Presidential Lecture Series at Purdue University this evening. We are a community of scholars and curious minds, and it is a delight to welcome tonight's speaker and lecturer, Professor Moungi Bawendi, who not only is a recipient of the 2023, so last year's Nobel Prize in Chemistry for his pioneering work in quantum dots, but also is a proud alum of our very own public school system here, the West Lafayette Junior Senior High School. We're in a special treat tonight, starting actually with an actual lecture before the fireside chat with me. I tried to learn from his 1993 paper to ask questions. I hope he wouldn't give me a quiz at the end of his lecture presentation first. Please join me to warmly welcome back home Professor Moungi Bawendi. Thank you so much.
Good to be here. Good to be here. I'm glad to be here. And I'm not going to give a concert. This is just a prop to illustrate a few things. There's a screen back there. So I'm going to tell you a little bit before we start our conversation about quantum dots and what they are and how this Nobel Prize came to be. And so this is basically part of the origin story of the field that I'm in. Before it existed, before nanoscience and nanotechnology actually existed. And as the Nobel Committee said, these materials are the seeds of what we can now call nanoscience. And quantum mechanics is kind of magical. I love quantum mechanics. Things that are quantum mechanical have properties that are really non-intuitive. And this material is beautiful in the sense that it allows us to see quantum mechanics with our eyes in a very simple way. That's why I fell in love with it. What I got the Nobel Prize for was the synthesis of these things, and the ability to make these quantum dots in high quality really was what unlocked our ability to use them, to study them, but also all the applications that came afterwards. So let me tell you what a quantum dot is first, before we start, and why quantum mechanics is important there. So when we think of an electron in a circuit or in a wire, we think of a little particle of charge that moves around. We know exactly where it is at every time. We can see its velocity, its position. But we know that an electron in an atom behaves completely differently. An electron in a hydrogen atom isn't a particle that moves around the atom. It's there all the time. It obeys what we call atomic orbitals. And that's quantum mechanics. What happens if we take that electron and instead of putting it in an atom, we put it in a little box, like a nano box? We squish it down. When you can take an electron, you squish it into a little box, it's no longer a particle. It no longer obeys the laws of classical mechanics. The uncertainty principle comes in. You cannot anymore know its position and its velocity at the same time. And it behaves like a wave. The properties that it requires are those of waves. And so everything that is beautiful about quantum dots has to do with these wave-like properties of the electron. The nanobox are our quantum dots. We call that quantum confinement. I like to call it quantum magic. It's the magical properties of quantum mechanics that we begin to manipulate and see with our eyes. Now, we know a lot about waves already. Intuitively, we know a lot about sound waves. We know that a flute has a lower pitch than a piccolo. And why is that? It's because the sound wave in the flute is a longer wave than a piccolo. So we know that pitch and wavelength are associated with sound wave. You also know that if you look at organ pipes, small organ pipes have a higher pitch than a big organ pipe. And I brought the ukulele here also to illustrate this with string instruments because it's even easier to manipulate with a string instrument. So like this ukulele has 4 strings. They're all the same length, but they have different pitches. If you take any one string, like this one here, if we make the string shorter, by changing the length of the string, we change the pitch. The longer the length, the lower the pitch, right? So the vibration, the wave, gets shorter, higher pitched. A different string, we have the same principle, but in a different set of pitches. The quantum dot is, the electron, the quantum dot is the same way, right? So you put the quantum dot in a box, a small box, higher pitch, big box, lower pitch. Pitch for electrons is energy. Small box, the electron has high energy. Big box, it has lower energy. You change the inside of the box, you cover a different set of energies. Just like the different strings in the ukulele are made differently, they're stretched differently. They're the same length, but you have different pitches. So depending on the material, you can manipulate the pitch that way too. So the material and the size becomes our knobs that we can tune. They're very small, so we can't see them with an optical microscope. They're much smaller than the wavelength of the light, so we need an electron microscope. That was my student at the electron microscope about 10 years ago. And this is what they look like. They're little tiny particles, about, in this case here, 3 or 4 nanometers. In this case, cadmium selenide, 2 elements, cadmium and selenium, that make up the semiconductor. Nanometer size, and they show these beautiful quantum size effects. How do you get that electron in your nanobox in the first place? You know, for the ukulele, I struck the string and I created the wave. In a flute, you blow into the flute, you create the wave. The same thing for the organ. You send air through the organ pipe and you create the wave. Here we create the electron. We put the electron in here by striking the particle with light. Just like I strike the ukulele with my finger, and the energy of my finger goes into creating the wave. The energy of the light displaces an electron that was bound to one of the atoms and liberates it to occupy the entire box, the entire nanobox. That's how we get that one electron to fill the box. Eventually, that one electron will want to go back to where it was. So the energy of that liberated electron, when it goes back to where it was, that energy, it comes out as light energy, which is also a wave. So a small wavelength electron in the box creates a small wavelength of light, which is to the blue, and a longer wavelength electron creates a wavelength of light, which is further to the red. That's the quantum confinement, the quantum magic that you see with your eyes now. The color of the light tells you where that light came from and tells you about the properties of the wave, electron wave, that created it. And you see that in fluorescence. So these vials fluoresce because they've been excited with UV light, and they fluoresce back and show you what that electron wave was doing. Now, the Nobel Prize was given for 2 things, according to the Nobel Foundation: the discovery and the synthesis of quantum dots. And let me tell you a little bit about the discovery. So the discovery was by Lou Bruce and Alexei Ekimov, working in 2 different parts of the world at the time, in the US and the Soviet Union, separated by the Iron Curtain. This was the Cold War, the early 1980s. Lewis was interested in understanding the transfer of electrons from semiconductors to molecules in liquid, where these electrons were generated by sunlight. So the energy of the sun comes in, liberates an electron in the semiconductor. That electron carries the energy of the sun and does electrochemistry in solution to create perhaps a fuel. It was the energy crisis of the late 1970s under the Carter administration, the OPEC embargo, the creation of the National Renewable Energy Laboratories. So there was a lot of people working in that area. And he was interested in the kinetics of how fast does an electron go through that interface between the semiconductor and the solution. And in order to be able to have better signal to noise, be able to study that better, he decided to make the chunks of semiconductors smaller and smaller and smaller to get the surface to volume ratio higher and higher to increase the signal. He was doing this at essentially room temperature in water, creating these particles of cadmium selenide from cadmium salts and hydrogen sulfide. This was cadmium sulfide. And he found that when he got to small enough sizes, the experiment became, in a way, irreproducible, or he got a different color every time he did the experiment. And then when he let the sample sit, it seemed to change color. It became more red, more towards longer wavelength light. And he questioned that. He asked, why is that happening? What's going on here? Initially, he thought it was a classical effect called Mie scattering. The same effect as to why the sunset looks red. Particles of micron-sized particles will scatter blue more than they scatter red light. And in the sunset, you see the red light because all the blue light is scattered. But those particles are way too small for that. They're so much smaller than the wavelength of light. Scattering from light doesn't do anything. And that's how he came up with the right explanation, which was that it was a quantum mechanical effect, quantum confinement. Wrote a paper about it in 1983, and then a series of papers explaining this new effect that he had discovered. Ekimov, across the Iron Curtain, was interested in colored glasses, like in old churches and cathedrals. What gave the color to these beautiful glasses? It was already known that the red is due to small particles of gold. When you make gold and you break it up into tiny, tiny pieces, it doesn't look like gold anymore. It looks like this beautiful red color. And Faraday in the 1700s, late 1700s, already knew that. Some of his samples are still in the Cavendish laboratories. But the other colors, there were these recipes that contained all sorts of heavy elements that had to be active in creating the colors. So he got rid of all the extraneous things, or what he thought was extraneous in those old recipes, and kept the heavy elements and began to manipulate the glass by heating it and cooling it, and was able to show or convince himself that the same elements he put in there could create different colors. And then using the tools that he had, small angle X-ray diffraction at the time, he was able to correlate size and color, just like Lewis was able to correlate size and color by using a transmission electron microscope and actually seeing the particles. And he wrote a paper in 1981 in Russian, which wasn't translated until 1983 or 84. And so they discovered this. In fact, the two papers have the word quantum confinement in them. The same discovery at essentially the same time across two different parts of the world. Is this a coincidence, or was the world ready for that? I think the world was ready for that, actually, given where they were studying. They didn't know each other. Lewis eventually found the translation of Ekimov's paper in the mid-1990s and wrote him a letter saying, we should communicate. We're working on the same thing. His letter was intercepted by the KGB. And KGB paid a visit to Ekimov and another guy, Efros, that we work with, and to ask them, why is this American scientist interested in what you're doing? What are you doing that's so interesting? Eventually, both Ekimov and Efros, who were visited by the KGB, emigrated to the US in the early 1990s after the fall of the Berlin Wall. So that's the origin story. Where do I come in? I come in through the synthesis. The samples that Lou Bruce was making were made at room temperature. They were not crystalline. They were highly defective. They were made in water, and these materials actually don't like water very much because they tend to turn into the oxide. So cadmium selenide tends to turn into cadmium oxide, a completely different material. And I started at MIT, and my project was to create, a series of sizes to understand the evolution of properties from atomic to macroscopic to bulk-like, how these electrons change, how the materials change. And I had stumbled into a preparation at Bell Labs that seemed to work. I came to MIT, and this preparation that seemed to work some of the time, to give one size at least, stopped working. Occasionally at MIT, at Bell Labs, became never at MIT. So I had to re-engineer the whole process of creating particles, these particles, so that I could study them. Hence this synthesis that was really out of necessity to study the basic physics that ended up unlocking this whole world of nanoscience and nanotechnology. I knew from what I had done at Bell Labs that there were two important things. One was the concept of nucleation and growth, and the other one was high temperature, and some molecules to prevent the growth from being out of control. Nucleation and growth, it's a very simple concept that we all have an intuitive feel for it. You know when it snows, and it's very dry and cold out, the snowflakes are all very small. The clouds create little tiny seeds of ice, and those tiny seeds of ice go down, and if there's no more water to aggregate on them, they come out really small. If you have a warm, humid day, it's a lot of humidity, a lot of water molecules out in the atmosphere, as these ice particles come down, they aggregate more and more water molecules, they grow, and we end up with big, fluffy snowflakes that are all about the same size. So the same idea here, seed something with very small particles, and find a way to let it grow so that they all grow roughly at the same rate. We also had, since we were chemists, we also had a final process where we purified our sample. We created a purification process which allowed us to further narrow the distribution of sizes to really get to particles that were really essentially all the same size. And this process is called a hot injection synthesis. We didn't call it that, that's what people called it later. And this was my first paper that I wrote as an assistant professor at MIT. I thought nothing was working. I was going to not get tenure, lose my job. But I had two great students, at least I had three great students. The two that worked on this were Chris Murray and David Norris. That are professionally very renowned today. And Chris was the synthetic guy. David was going to be the physics guy. And he wanted samples, and Chris was going to make them. And so they ended up working together to create this process. And what you see here on your screen is a flask with a syringe that has metal organic precursors, meaning they're really air-sensitive materials that contain the elements that we want to have in there. They're ready to react with water and air, but we knew water was not something we wanted to have anyway, so everything here is done under nitrogen. The solvent is at very high temperature to get good crystallinity. At room temperature, these molecules that contain cadmium and selenium are stable. You introduce them very rapidly into this hot solution. They break apart, and they begin to react with each other, making the small seeds, in this case of cadmium selenide. When the concentration goes down to a certain level, they don't nucleate anymore. The clouds only nucleate when it's very concentrated water up there, otherwise they stay as clouds, it doesn't rain. Same idea here, but there's still a lot of precursors around, so they keep growing on top of the seeds, and you end up with this thing. It's a very simple process, which turned out to be really important for the applications later, because it's easy to scale up, and it's not expensive. So I have a video here. This is what the flask looks like. It looks like the cartoon. This is still the way we make them in the lab. And you just scale this up by a couple of thousand times, and you end up with what is done commercially. And this is the video of what it looks like. So there's a syringe with the precursors. And he's going to inject them. The student here is going to inject them. This was made in 2010 or so, this video, into this flask at 350 degrees Celsius. It's hot, quick injection, sudden color change. These are the seeds. These are 1 nanometer size seeds of the material. He's going to take samples out to show us the growth that we can see by eye of this quantum mechanical process. And I'll spare you the 20 minutes of growth here and come back. And there's a much darker color now. The particles have grown, like the snowflakes have gotten bigger. Still taking samples out. Now we can see what they look like when light goes through them. The greener color ones are smaller, and the bigger ones are the redder or the yellow ones. And then he's going to put a UV light on them, essentially to convert the energy from the light to electron waves, which then fluoresce. And that's really the story of the synthesis. And after that, off to the races. That was 93. 98 was the first company. And then, here we are.
Well, Moungi, I would like to come back to some of the details of that discovery of synthesis. But I got to ask, this question has been asked so many times over the past 6 months. Where were you when you got the news?
I was in bed. I was sleeping soundly. It was 5:30 in the morning.
Okay.
Yeah.
And what was your first reaction?
I was kind of asleep.
They don't respect your sleeping pattern.
No, they
right? These phone calls from
they
Sweden.
really don't. And so the phone rings, and the first thing you think when the phone rings in the middle of the night is something bad's happened, right? And we had the ringer on because, we have older parents and stuff like this. You never know. In the middle of the night, you get a call, right? My wife sits up and says, "What happened? What happened?" And I recognize the Swedish accent, right? And I tell her it's Stockholm. And then the day becomes like this, and that's how it starts, and it's all chaos. And they ask me, so I'm half awake, and they say, congratulations with Alexei Ekimov and Lou Bruce, and I'm like really confused. Why am I part of this group? I didn't discover this.
Oh, well, you're too humble. The synthesis, one could argue, is even more important, perhaps, or at least just as important
It's
as
part
the
of the
initial
story.
identification. Yes. Well, now you were born in Paris.
I was, yeah.
And then you grew up here in West Lafayette. I heard it's in part because of your father, who was a faculty member here in the math department.
Right.
Is that right?
That's right, yeah.
So when did you arrive in West Lafayette?
So we arrived when I was 10 years old in 1971. Yeah, my father was Tunisian, and he was educated in Paris, in France. Met my mother there, and went back to Tunis. So I grew up in Tunis for a couple of years as well. Then we went from Paris to Tunis, then to Nice. But it wasn't so easy for a Tunisian to have a permanent academic job in France at the time. But the US was welcoming, and he found a place at Purdue, and it was a wonderful place to move to and to grow up.
Oh, wonderful.
And, yeah.
So you were 10 years old. So was it the intermediate school that you started enrolling in?
I started at Brooksfield School. I think does it still exist?
Oh.
No. Yeah, so in sixth grade.
Sixth grade. And
Yeah.
then you enrolled at West Lafayette Junior Senior High School, which still do exist today and is ranked number 5 out of 10,000 schools in the United. I don't know how they're ranked, but it sounds good.
System.
So was it that good when you were there too?
But at the time, the junior and the senior high school were separated.
Oh, okay.
It was a separate school.
So
separate buildings.
You went to the senior high school.
I first went to the junior high school.
Oh, junior.
And the
I see.
high school. And then I went back to France for a year.
Oh, is that right?
As a freshman in high school, yeah, and came back here.
And then you came back here. All right. So you were like.
I was nomadic. My parents were nomadic. And as a child, I just had to follow.
Is that sabbatical year that you
No, they thought they were going to go back to France.
Okay.
Permanently, but it didn't work out. So
well, we're glad that you came back. And so you were there in junior high school, I guess the 7th and 8th grade. You were back in France for a year. You're back here for 3 more years of high school. All right, now we're very clear with your growth trajectory. And what was it like when you were a student in our junior and then senior high school? And did you have an amazing chemistry teacher, or did you start liking chemistry back then?
So that's a planted question. I had a great chemistry teacher, James Guy, Mr. Guy, we called him. And I don't know what it was about his teaching, but it just, really clicked. Yes. Really clicked for me and inspired me to stay in chemistry.
I know that you started writing the new editions of the famous textbook, Physical Chemistry. Right? I'm wondering, is that something that got with this inspiration that you had, got to do with that when you were a student, that you want to educate in part through this standardized textbook for many generations and inspired in part by your high school teacher?
So yeah, I love teaching, and that's why you go into academia. Research and teaching are two things. And the textbook started in the 1950s when Alberti took it over from somebody else, and Silby came in the 70s, and they were both getting older. Alberti was retiring from the textbook, and I was brought in to to replace him. And I thought, what a great idea. You know, it's got all the physical chemistry that I love, quantum mechanics, statistical mechanics, thermodynamics.
Yes.
Yeah.
Wonderful.
So I
You
came
know,
on board.
I don't know about you, but I was able to learn a lot from your 15-minute presentation just now, the clarity and the analogy and anticipating questions that you may have. I've had some amazing teachers in my own life as well, both in K-12 and then at Stanford when I was a student and undergrad there. And there's this amazing faculty, Tom Cover, and then another one, Stephen Boyd, both electrical engineering.
Oh, yes, I know Steve Boyd, yeah. I know Steve Boyd, yes.
It is just stunning. It was a beauty to sit in there and listen to how these giants in the field of teaching and research explain concept. And later in my own career, I tried to say, can I explain the same concept, simple, something like least squares, in any better way, more succinct, more to the point, more anticipatory of any questions from all kinds of students? I couldn't. It is amazing. They both wrote also the standardized textbooks in the field. And just reading that textbook, you know, is way better than watching Netflix movie. This pure joy. Now, what was Purdue like? So you're a child of the Purdue faculty in the math department. You were in high school here. You live now far away, I assume. So did you participate in some Purdue activities?
I actually did. So I took classes at Purdue when I was a senior in high school.
You are alum.
I am an alum in a way, yes. Yes, I took math classes at Purdue. Yeah.
Not from your own father?
Not from my father, no. I took German at Purdue too, because German was a required language for chemistry until soon after I stopped, soon after I got my before I got my PhD.
Okay.
So you needed to have some knowledge of written German, so I took German at Purdue. And then I also was able to work in the chemistry labs.
You did?
I did. John Grutzner, who's sitting here. So I worked in his lab, and that was the beginning of my research career, right there.
Wow, that is amazing. Well, if you're a student sitting out there or getting the streamed version of this, and a student at the West Lafayette Junior Senior High School, please consider all the opportunities that this university offers to you. That's all the commercials. Now, so let me ask you some questions about your synthesis. But first, I have to confess that when I was a freshman, I was thinking of being a math or physics major, and I ended up being a math and electrical engineering major. But I took the sequence in freshman, and a little bit out of order. So I first took this quantum mechanics class in the fall quarter. And the professor who taught us, freshman, he ended up receiving Nobel Prize in physics.
Oh, really? Wow. Yeah, nice.
So we're like, oh, okay, this is like, not bad. I'm a freshman here. I don't know what's going on in the class. But our professor just got Nobel Prize. But turns out that he needed to spend a lot of energy and time to prepare for his Nobel Prize speech. And he told us about 2 weeks before final exam that he's not going to have time to design final exam for us. And I guess it's the right prioritization there. And therefore, everybody will get an A.
Wow.
Now, we don't do grade inflation here at Purdue. But we were like, at least
great.
I was one of those students, because I had no idea what he's talking about the whole quarter. I said, great. Well, I'm one of those students without motivation. I couldn't study, so I stopped learning quantum mechanics. So to date, anytime I see the word quantum, I shiver and say, I don't know what I'm talking about. So you have to pardon my ignorance. But this is the paper, 1993, in Journal of American Chemical Society, the synthesis and characterization of nearly monodisperse, cadmium and other semiconductor nanocrystallites by Mary Norris and Bawendi as the correspondence author. And figure 3 in particular was cited heavily. Well, you can't see it from here, but this is the figure that shows on y-axis is the absorbance, and x-axis is the wavelength, and you've got about 10 or 12 curves corresponding, starting from about 1 nanometer to about 15 nanometers there with the pattern. And you already told us sort of how small they are, these nanoparticles. Just how small are they? to the layperson?
Sure. So, a molecule has a few atoms. A nanoparticle has about 100 atoms. So they're basically the size of a protein, a big protein. So in fact, the first application, because we were chemists and we knew these are roughly the same size as biological molecules, was in trying to use them to tag cells and in vivo also to look at the fluorescence that would come out if we could direct these things to particular parts of cells or tissue.
Now, in the late 1980s, did I remember this correctly, that you had a couple of years at Bell Labs?
Yes. Yeah.
And with one of the two, the American discoverer of the physics and the chemistry of it before the synthesis. And what was lacking back then in the late 80s or early 90s? Sort of, what was that aha moment that you discovered in the synthesis?
Science is a series of failures, pretty much, and you overcome the challenges. So when I was at Bell Labs with Lou Bruce as a postdoc, I had discovered accidentally this way of making them a little bit better than they had done before. Mm-hmm. And that's when I realized, I was doing nucleation and growth. It was kind of an accident that I was doing that, and raised the temperature and moved from water to not water. But still, I started with a water solution. Basically, if you're going back to this analogy of the seeds being formed in a cloud and then falling down and aggregating, I was making little seeds in a water-based solution, taking those little seeds and transferring them to a non-water organic solvent without any air, et cetera, in them, and then growing them in that. But there was still some water that was being carried over, some oxygen, and so that made it very irreproducible. And I think in retrospect, that's why when I went to MIT, things didn't work, because having this first step in water was just a terrible idea. And so taking the step of just getting rid of the water complete, that step, figuring out how to do the nucleation directly in the growth solution, that was really the key step. And then switching completely to air-free chemicals.
I see. Well, I can see there are so many different parameters here, solvent being one of them, and the temperature, another one, right? And also what people refer to as the temporally discrete nucleation and the growth and the annealing phases. So it sounds like it's a space of many degrees of freedom. There are many possible combinations. So did you try many different combos?
So I actually didn't try anything because I was a professor then.
Yes, you have students.
I had Chris Murray and David Norris.
Okay. How many times did you altogether try before you hit the right combination?
So actually, as an assistant professor, I was still working in the lab. It's in the lab with them.
Yes. After tenure and a full professor, then you really got an army of people.
Yeah, and then you don't have the time to work in the lab. But at the time, I was still working with them in the lab, and had 2 extra pairs of hands. We went through a lot of permutations. It was really trial and error. It was really an Edisonian process, guided by intuition from what we knew from the old literature from the 1950s of nucleation and growth. And just intuition, really. And I don't know. So the process that we came up with is actually very similar to the way that Ekimov made his particles in molten glass, right? So he stumbled across essentially the same thing. He would have elements in glass, and he would really quickly heat up the glass and then cool it down and quench it, right? So the elements would then begin to react in the hot glass. When you quench it, they freeze in place into small particles. Then he would slowly raise the temperature again and allow motion of elements again in the glass. So not that different from except we were doing it in solution, right? And we can then take the particles out, we can purify them, we can do all sorts of games with them, we can put them in polymer, put them in TVs. I don't know if these have quantum dots in them, but they very well might.
They might, although we have
Depends how old they are.
a budget constraint of freezing tuition, so usually our hardware is a few generations behind. Now, you mentioned this intuition, so it is not just exhaustively searching through this huge combinatorial space either. And I've heard sometimes people have intuition when they're at a particular moment. Like when they're listening to Brahms, when they're taking a walk in the garden, when they're sitting under an apple tree and got hit by an apple, etc. So were you doing something specific, washing dishes, cooking something, or brushing teeth?
I don't remember when the intuition came. Usually it came when I was running. Your mind just, you're breathing, you think about your breathing, and then you think about the problems that you might have. And then it just, your body just does something very mechanical. And yeah.
Running is good indeed. Well, actually, yesterday is Purdue Annual Day of Giving, and I started running with the students for fundraising for student organizations. Well, that didn't clear my mind. All I was thinking at that moment was, how can I keep this pace before collapsing on the ground? So where are we ending this running here? Now, back to the 1993 paper here, right? And by the way, it was published in March 1993 for historical accuracy purpose. Was it discovered, the experiment itself, was it 92?
So the hot injection was in the fall of 1990.
When you first started
When I
at MIT.
first started. So when I talked to Chris, in my mind, the period where nothing worked, in my mind, lasted for many years. But the reality is only lasted for a few months. When I went back. So I started in July 1990. Nothing was working, So September, the students start coming, nothing works. And it was November, December 1990 that we hit upon getting rid of the water, doing this hot injection. And at first, the material wasn't great, but that was the breakthrough, right? And then from 91, so January 91 to mid-92 is when we optimized things and perfected things. Then Chris learned how to use an electron microscope. He didn't know how to do that, all these things that needed to be learned to make it go forward.
Wow.
And then it takes time to write a paper.
Yes.
Yeah. And to submit it and to go through the review process.
Yes. Depending on the reviewer, that can take a few years. This is a wonderful journal, apparently. That didn't take that long, but it is truly an Edisonian, as you said, perseverance there. Now, when you worked with your students, and you were a student yourself and then a postdoc at Bell Labs, any advice on mentorship?
Well, I view being a graduate student or a postdoc as a kind of apprenticeship. So you're working closely with the mentor that you have, or the older students, or what have you. And what you're trying to impart is the ability to become a scientist, to ask the right questions when you're faced with a challenge, have the perseverance to solve the challenge. And then when it becomes too hard, realize that you go to a different direction. Or if you discover something accidentally, stop doing what you were doing and follow a completely different direction, right? Because that could be a lot more interesting than what you were thinking you were going to do initially. And that process is really by osmosis. It's by watching, by taking part in it. And so you have to have patience and have lots of conversation with the students. And that's the way that I think is science, or the way of doing science gets transferred.
And what are you and your students working on right now? You mentioned some applications of quantum dots. And indeed, the nano world has been exploding to a large degree thanks to a scalable way to synthesize.
Yes.
So what do you see as the most promising next set of applications?
So what I'm interested in, so there are many applications, but I can't do everything, and I'm not very good at a lot of things. I'm only good at a few things, and one of the things I'm good at is quantum mechanics, like this thing here. So I'm interested in the application of the light from these particles in quantum optics, quantum communication, quantum computing, these sorts of things as the feedstock for doing these manipulations, these quantum manipulations. But other people that are more chemists than I am view catalysis, photocatalysis, very similar to what Lou Bruce started at, trying to make fuels from sunlight using semiconductors. But now we know so much more. 40 years later, we know how to manipulate the material. We know how to make it much more stable so that it can survive the harsher environments. And I think these photocatalysis directions are potentially really interesting directions to go. I'm not going to go there, but a huge number of the communities are going that direction.
Yes, it's part of the core joy of being a faculty member, I guess. We get paid to learn.
Oh, yeah.
We can always try new things and so on.
Yeah.
I even get paid not to learn too, but I get to learn from the very best in preparing for each presidential lecture, especially with the leading scientists of our time. I try to read up some papers, and then I get great lectures from our own Purdue faculty, chemistry faculty. For example, in this case, I cannot pretend I fully understood what I was taught, but we have great faculty and great students here at Purdue. In fact, we're going to save some time now to turn to our students to ask some of the questions.
Great.
Let's see who's got the mic there. Yes, please.
Hello, my name is Lauren Kale, and I'm a junior studying chemistry and materials engineering. Thank you so much for your time. Thank you for this opportunity. Your first question is where and how have you found your biggest support system, and how has that impacted not only your career, but your education as well?
Okay, that's a difficult question, my support system. I mean, part of it has, my family was really my support system from the very beginning, even through graduate school. My parents, that was my support system. Because when we were moving around so much, I became a little bit of an introvert, and I never felt like I fit in. So I never really built much of a support system other than my family. But now I have a much bigger support system. I have a community. And so, yeah, it's very different now.
Thank you for the question.
Yeah.
Thank you, President Chang and Dr. Bawendi, for this opportunity to ask you a question. I'm Olivia Snell, and I'm a freshman majoring in biochemistry through the Department of Chem. And my question for you is, do you see quantum dots being applicable components in the field of medicinal chemistry and maybe even in radiopharmaceuticals?
So I've applied quantum dots for imaging in animal models, and to understand and to use what we learn from the dots in these models to learn biology. And I don't think that they're going to be applicable to humans, but I could be wrong. Although we've translated what we've learned with the dots that are made of heavy metals to magnetic particles, iron oxide particles, which we learned to make really, really monodisperse that may have applications in magnetic resonance imaging that could be translated to humans. So there are many possibilities. I'm just not smart enough to see them all. But some other people might end up doing it.
Thank you for the question.
We have one more question for you tonight.
Please.
And this is from Abby Sullivan, who's a student in the chemistry department. And their question was, how do you envision the relationship between chemical research and academia and industry evolving in the future?
Well, I've seen a lot of changes since I started my own career. At the beginning, this was, in the early 1990s, this was before sort of the explosion of startups and the transfer of research to commercialize it. The growth of patents from universities. And we see more and more collaborations and the transfer of students from universities to all sorts of companies, even if it's not chemical research, in all sorts of directions. I think that because of the way funding from government sources is decreasing more and more, the ability to fund basic research from governments is much less than it was 30 years ago, significantly less. The requirement of getting money from the private sources, becomes much more important. And so I think that we'll see the impact of that in the future. Maybe research will be guided in different directions because of that. It'll be guided by what industry is interested in rather than what government might be interested in. But I think we'll always find room to do fundamental curiosity-based research, one way or the other. We'll find a way and discover new things.
If I may tag along the student question here, because earlier this morning we had another presidential lecture series. We usually don't do two in the same day, but the scheduling turned out to be so. And with Senator Todd Young and Dr. Punch, Director of National Science Foundation, and we were discussing this. Perhaps it's a false trade-off, but it's a valid question, legit question to ask. The potential trade-off between basic research and applied or use-generated or use-centric research there. And your own research, I guess, is an interesting bridge, right? You were working on a scalable synthesis based on the discovery. And I remember some debates in the mathematical community. I'm sure your father had his opinion on this. Is mathematics discovered or created by human beings? Now, in science and in engineering technology, there's also this question, some people would say, if you're in science, then you discover things, analyze, and how they work. And if you're in technology or engineering, then you do synthesis, you design and make things. Clearly, you need both, but your own work is an interesting combination of both, right? So what's your view on this basic versus applied and the potential trade-off between or choice between discovery versus creation?
You have to have both. The discoveries of today are going to be the technologies of in 30 years. So if we don't fund basic research today at an appropriate level, which we are not doing today, we're robbing future generations of technologies that could change the world. And so we need that. The quantum dots initially was a curiosity-based research. It was how does material change from the atomic to the bulk-like? That was the curiosity research that I wanted to study at MIT. I had no idea about the applications. This was totally not application-driven. And Lou Bruce himself says he would never have been able to get NSF money for what he was doing. He happened to be at Bell Labs. It was easy to be funded at Bell Labs. It was
at that time.
At that time, because it was part of AT&T, which was a monopoly, a regulated monopoly. They didn't care what was going on at Bell Labs. There were all these discoveries. They had no idea what to do with them. Other companies ended up commercializing them, like the transistor or the solar cells, and things like this. But we don't do a good job of helping curiosity-based research, flower, and that's our detriment.
Yes. And while each individual at a given time may have to make a choice, an institution certainly can be supportive and appreciative of excellence in different forms and shapes.
Yes.
We talked about the use-centric type of research quite a bit earlier today at the other venue. But I always remember my other co-advisor, Tom Cover, he often would say, well, I don't want to write a paper proposal. First paragraph says, driven by certain applications, so and so. He said, A, I don't think that's true. My research and that application, they're not really related. And B, I'm very proud that what I'm working on has 0 applications whatsoever. None that I could see, but it certainly is fun. And as an institution, whether it's Purdue, MIT, or Bell Labs, I guess institution is a large place. It's a big tent. You can have excellence.
You can have both. So I agree with only part of that statement that he said, that it's true that writing proposals forces you to say things that you're just not sure at all. You probably even think that it will never happen because you have to make a connection with applications somehow. But I actually like the process of taking the basic science into applications. That's something that I enjoy.
Yes.
To see where it goes. You discover a new phenomenon. You discover a new phenomenon through your curiosity-based research. what is it good for? I mean, that's the next question. That's a really great question, too, that I think I really quite enjoy.
Yes. Well, there's another debate usually between theoreticians and experimentalists. And from a university budget point of view, we all know recruiting theoreticians and experimentalists are quite different cost equations. But, we got to hire the very best and retain and support the very best, whatever the areas might be. Now, some folks are saying that on the experimental side, and maybe even on the theoretical side, that AI not only has its many other applications in society, but also may change the way that science is conducted, starting with experimentalism, maybe even into theory, in the sense that sometimes the AI, allegedly, according to some of the folks out there, could help you optimize the way you do design of experiments. Do you see that coming?
I mean, there's some examples of AI basically being able to do things that we can't do, like AlphaFold is one of the examples of protein folding. The protein folding problem was a problem that so many people worked on, and this program, AlphaFold, this AI program, is able to generate protein structures based on looking at the entire knowledge of the sequences and how they fold in a way that a human wouldn't be able to do. But those are very specific examples. We use machine learning in my group to help us with acquiring data much faster. Basically clean up the noise and interpret data. And so I view machine learning as something that is essential for the new generation of scientists to use as a tool. But I don't see it being smart enough yet to replace the creativity of humans. I was listening to a podcast recently from a writer saying that the first draft is so hard when you're a writer, but it's where you create. And if you take that first draft and you make it AI write it, you've lost the creative process. And the AI only looks backwards. It doesn't really necessarily create the way that a human would do the hard job of creating something new.
Well, yes, they are very good at following rules, not as much in breaking rules. In the last few minutes here, I want to come back to West Lafayette Junior Senior High School. I know that you went back to your alma mater earlier this morning and had a set of conversations with teachers and students today. How's your impression in terms of the differences between now and you are a class of 1978?
78, yeah.
And so back in the 70s, how has your alma mater changed or not?
Oh, it's changed a lot. It's much bigger. It's beautiful inside. There's all this technology that wasn't there before. The classrooms are incredible.
Swimming pool?
So we had a swimming pool, but it was much smaller. It was a smaller swimming pool. I mean, the environment looks so incredible. And the students are really excited. I mean, I'm so impressed by the questions that I got from the students there. Really, it's really great to see the next generation. The world is in good hands.
Well, especially here in West Lafayette Junior Senior High School. One more commercial for the great school here we call Neighbor. Now, I always ask this last question to all the presidential lecturers. What was the most stressful moment or disappointing moment that you struggled through? And I can tell you mine first while you think about that question of the last resort. For me, it was, at least in recent memory, it was just last month during the men's basketball March Madness. And not the later games, not the national championship game that we made to, first time since 1969, when you were right around here at that moment, right?
Not quite yet.
Not quite almost. But yes, it's a great team, winning a season in our program history, and the team conduct themselves so well both on and off the court, reflecting our academic orientation and the character and the values of Boilermakers. But it was the first game of this March Madness, because there's a lot of pressure due to what happened to the first game a season ago. And so I was thinking, oh no, we got to win this one. We have to win this one. And it was also in Indianapolis, surrounded by Boilermakers. Yeah. I'm proud to say, not only we won the game, we won it by a large, large margin. So, but it was very stressful the night before. All right, that was my answer to the question. So what was your most stressful moment?
Yeah, I can't compete with that. I don't think, there are so many stressful moments in life,
Our most disappointing moment in your career, let's say, maybe when the 6 months pass and nothing's working.
That was, yeah.
Thought you were going to lose.
It wasn't a moment in time. It was a stretch in time where nothing was. This really was the most stressful time in my life. Where I started as an assistant professor. This is my career in front of me. This is what I want to do for the rest of my life, and it refuses to work. That's incredibly stressful. And, then you develop this sort of imposter syndrome. You can't do anything. Nothing is working. You don't belong there.
Well, Neil Armstrong allegedly got once a C in his calculus homework. It's in the archive right here as a Boilermaker. And he was able to land on the moon. So I guess there's hope for all our lesser mortals here. And listening to you, Moungi, when you were assistant professor, just starting out, and how many years was it for the tenure bid back then at MIT?
At MIT was 7 years.
7 years, all right. So, and nothing was working. The imposter syndrome feeling, all of that. And yet, right around the corner at that time, boom.
Yeah, unexpected.
Unexpectedness, I guess, visit those who are determined and prepared. And then the 1993 paper, they changed the way that we human beings interact with the nano world. Give it up for Moungi Bawendi. Thank you so much.
Yes.
Thank you so much. That was great. That was great. Thank you for spending time with us. And from here, West Lafayette, Indiana, Purdue University, good night.